Okay, here we go. Solutions. Have you ever wondered why a raw egg swells or shrinks when placed in different solutions? Well, we're going to go through that today and actually get into it more next time. So hopefully this will help you to understand that. We need to go through some definitions first. Some of the definitions are what a solution is. Well, it's a mixture of two or more substances in a single phase. One constituent is usually regarded as a solvent and the other as a solute. Well, what is a solute and a solvent? A solute is the thing being dissolved, and a solvent is the thing that's doing the dissolving. So a solute plus a solvent is a solution. Most people think of solutions as just being liquid. They don't have to just be liquid. So over here on this side, you can see the different states that a solution can be, and then what the solvent and the solute could be. And here are some examples. One that you're probably using a lot is a liquid one, which is liquid and gas, which is pop. So how does a solution form? As a solution forms, the solvent pulls the solute out of solute particles apart and surrounds them or solvates them. Okay, so what happens is here we have a sodium chloride molecule, and the water molecules, the hydrogen is white and the red is oxygen. Hydrogen is positive and oxygen is the negative side, that's the pole. This one has the oxygens all close to the purple molecule, which represents the sodium, and the Cl is represented by the green. And you can see how it pulls and surrounds them as it pulls it apart. You need to be aware though, just because a substance disappears when it comes in contact with a solvent doesn't mean that the substance dissolved. It could mean that a chemical reaction occurred. Dissolution is a physical change, not a chemical change. You can get back the original solute by evaporating off the solvent. If you can't, then the substance didn't dissolve, it reacted. So if I started here with some metal and I put in hydrochloric acid, and then when I evaporate off, I've got this, a chemical reaction occurred. Some other definitions we need to worry about are saturated and unsaturated. Saturated just means as much of the solute as I can at that temperature. Unsaturated means I don't have as much solute as I could have dissolved at that temperature. You've heard of saturated and unsaturated fats. Saturated fats are bad for us. Why? Well, saturated fats have hydrogen every place they could possibly have hydrogen. They're straight. Our body has a hard time breaking them down. Unsaturated fats have a double bond, at least one, that causes a bend in the molecule. Because of this bend, our body can get in here and break up this long chain and begin to use it for fuel. We also have what's known as supersaturated solutions. These contain more solute than is possible to be dissolved at that temperature. Now how do you do that? Well, there's two different ways you can do that. The first one you use in making candy. You warm up the solvent, which usually is water, so that it will dissolve more, usually sugar. Okay, then once you get it hot enough, then you can cool it down. This is where you make hardtack candy or taffy or suckers or divinity, those kind of things. You can also evaporate off some of the solvent, so the solute does not have solute has more than it's supposed to at that temperature. This is a type of solution that's supersaturated. It'll look clear, but if you touch it or add a seed crystal, is what we call it, then it begins to solidify quickly. A fun thing to do at home, if you have time, you should take 2 tablespoons of baking soda and you carefully add it to about 1 liter of vinegar. You know that volcano thing that you used to do in junior high and that for science? Well, you do that, but you do it slowly and you do it in a large pan. When it's all dissolved, then you're going to put it on the stove and heat it up till it boils, and you're going to let it boil there for a while. So we're heating off some of the solvent. As you start to see a thin skin appear on the top of that, you want to pour it quickly into a clean container and let it cool. Then once it's cooled, what you want to do is get a paper plate, and you can put a couple grains of salt or sodium bicarbonate, or sometimes they'll even work just with nothing. And you pour slowly that liquid that you have onto the plate, and it will start to form a a stalagmite or a tower of sodium acetate. Sodium acetate is also used in reusable heat packs where you can boil this. It's a plastic container. It has a little metal disc right here in the center that you click, and then that starts to form solid and gives off heat. So sort of fun. So there are some factors that affect solubility. If you use the axiom like dissolves like, then polar substances tend to dissolve polar substances, or ionic. Nonpolar, which are covalent substances, tend to dissolve nonpolar or covalent substances. So you've heard the saying that oil and water don't mix. That's because oil is nonpolar or covalent and water is polar. So when we have ionic compounds, what happens is when they put in water, they separate into their ions. And because they separate into their ions, they are called aqueous. Okay, so that means their water helped them separate into the ions. In aqueous solutions, we can know that an ion is present by testing with electricity. And if it conducts electricity, they're called electrolytes. Strong electrolytes are things that dissociate into ions completely in water. So HCl, MgCl, and NaCl are some of the strong electrolytes. There's also many more. If they don't dissociate in water and don't conduct electricity, they're known as non-electrolytes. This would be our covalently bound things, whereas our electrolytes are our polar covalent and ionically bound things. Now it's time to play everyone's favorite game show, electrolyte or non-electrolyte. See if you can guess them right. You've got them, if you printed out the PowerPoint, you've got them so you can quickly go and look and write down, do you think it's electrolyte or not? If you don't have it printed out, then just do it along with us. Sucrose, which is table sugar. Here's the chemical formula for you. What do you think? Is it electrolyte or not? Well, it's covalently bound, so it's a non-electrolyte. What about sodium chloride? Table salt. Electrolyte or non-electrolyte? This is ionic, so it is going to be an electrolyte. What about octane? This is gasoline. Electrolyte or non-electrolyte? Non-electrolyte. What about magnesium chloride? Well, it's a polar covalent, so it's electrolyte. What about calcium bromide? Again, electrolyte. Far apart on the periodic table is another way you can look at it. Oops. What about sand? Si. Those two are close together on the periodic table, so it is a non-electrolyte. All right. Electrolytes are really important. We have to have them in order to carry messages from the brain to the rest of the body. If you don't have the right amount of water to break down those salts, then our body can't carry the signals. If we have too much, then our body, and not enough water, then we can't do it either. So we have to maintain cellular function with correct concentrations of electrolytes. We have to have enough water, and we have to have enough salt. So a lot of times when we sweat, we get rid of a lot of the salt that's in there. That's why they say, drink Gatorade, it has great electrolytes, blah, blah, blah. Basically, you're just having some sugar or salt water, okay? We need concentrations. We have to keep track of how much of something there is dissolved in water. And so one of the concentrations we use almost daily in chemistry is molarity. Molarity is just taking the moles of the solid, dividing it by the liters of solution. That's it. We already know how to find moles. Moles is the grams divided by the mass of the substance. Now all we're going to do is take that and divide it by liters to get molarity. That's a concentration, capital M. Now to make a molar concentration, we usually use what's called a volumetric flask that looks like this. It has one mark on it right here. We don't fill this up with water first. We fill it up a little bit, probably down here at the bottom. We put in our substances we've weighed out, and then we fill up till the bottom of the meniscus hits that line. And we shake it up until it totally dissolves. If we did it the other way, where we put the water in first and then put the chemical in, we actually would be left over, we would have leftover water. And so it wouldn't be in 1 liter of solution. We wouldn't have enough. So let's figure out the molarity for a substance. Here we have 5 grams of nickel 2 chloride hexahydrate. Remember the hydrates and the formulas and how to name them? in enough water to make 250 milliliters of solution. And we need to calculate the molarity. So the first thing we need to do is change these grams to moles. So we're going to add up a nickel, 2 chlorines, 12 hydrogens, and 1 oxygen. We're going to take our 5 grams and we're going to divide it by that mass that we just added up. And we get moles. Now that we have moles, we need to take this 250 milliliters and change it into liters. Divide it by 1,000. And take our moles divided by our liters, and we end up with molarity. Now to report this, we don't stop here. What we do is we put brackets around the compound. The brackets denote concentration. And then we say equals 0.0841 capital M, which is molarity. All right, so using molarity. In lab, we often have to make up solutions. And so if I needed to make up 250 milliliters of a 0.05 oxalic acid, how much would I need to weigh out? Well, we rearrange the equation of molarity equals moles divided by volume to moles equals molarity times volume. We're going to take the moles equal to, first we need to transfer the milliliters into liters, so we're going to divide it by 1,000, get our liters. We've got molarity right here, and we just plug it through and get our moles. Well, I still don't know what the mass is, but I do know how to take moles and change it to grams. So I'm going to convert from moles to grams by taking the 0.0125 and dividing and timesing it by 990 and dividing by moles, and I get 1.13 grams of oxalic acid. And I can now weigh that out and put it in a 250 milliliter volumetric flask, add distilled water up to the mark, so the bottom of the meniscus. Okay, here's your learning check. You try now. How many grams of NaOH do I need to weigh out to prepare a 400 milliliters of 3.0 molar NaOH? Pause the video. Okay, we're back. How'd you do? Did you figure out it was number 2? Good job. There are 2 other concentration units that we're going to be worried about. First one is molality, and this is an italicized M. Molality is moles of solute divided by kilograms of solvent. And we use this specifically for large amounts. We're usually using it for outside of lab. And we also worry about percent by mass, or pph, parts per 100. That is grams of solute divided by grams of solution times 100. It's also known as pph. Sometimes I use this in water quality or in air quality. These are the ones you probably have seen more, is parts per million and parts per billion. When they report air quality, it's usually in parts per million or parts per billion. Parts per million is just the same, mass divided by the total mass times by 10 to the 6th to get it into millions. Parts per billion, same thing, mass of what you're looking at divided by the total mass times by 10 to the 9th. Pretty easy. This parts per billion and parts per million usually is seen on the core test, so make sure you're familiar with it. Same thing as pph, or percent. Now, if I were to calculate the concentrations here, I'm going to dissolve 62.1 grams, which is 1 mole of ethylene glycol, in 250 grams of water. What is the molality and the percent by mass of, or pph, of ethylene glycol? Now, ethylene glycol is used in antifreeze. So first of all, we're going to calculate molality. So we're going to take the grams, we're going to take the moles, and we're going to divide it by the 250 grams of water. Grams of water we need to change into kilograms before we put in, because it's moles per kilogram, and we get 4.0 molal, which we would use the italicized M. Calculate percent by weight, which is pph. We take the mass right here, add this mass and glycol's mass for the bottom, and then we times it by 100, and we get 19%, or 19.9%. Now it is your turn. Let's see what you do. Here's the possibilities. What do you think it is?